Hello everybody and welcome back to my Homework 2 Part D. I'm going to derive Broyden's method as an iterative refinement of an approximate Jacobian, and I can choose to do one of the two methods we did in class for deriving Broyden's method. So that's fun. I'm going to go ahead and choose sort of the easier way that my professor explained first. So, a quick review of what Broyden's method is. Last time I used it to compute the roots of a multidimensional function, as it talks about step size adjustment, that sort of thing. So it's a pretty cool function. It's pretty smart of Broyden, and there's a few things he did. But this is sort of the end product I'm looking at. I want to be able to show that, well, no, I don't want to show that. I want to show, I want to show this right here, that the Jacobian is just equal to my last guess for the Jacobian plus all of this stuff. So, with all that said, let me go ahead and I copy-pasted some of the definitions from Wikipedia into this paint file, but really all I'm saying is I have some independent variable x, and that independent variable is composed of a bunch of different values of x, sub-values of x, up to xk. And then I also have a function f, which is composed of a bunch of other functions going all the way to x, all the way up to function k, that are in terms of all the different independent variables x. Now, an important thing to note is that k is the same. So this is sort of a square Jacobian we're dealing with. The Jacobian has the same number of functions as it does variables to derive the function relative to. So if there's 3 functions, there's 3 different independent variables. If there are 10 functions, there are 10 different independent variables, and in that case the Jacobian would be 10 by 10. So anyway, with all this in mind, if I were to go ahead and take f and then evaluate it at some xn, and then I took that value and I added onto it the Jacobian evaluated at xn, and then I took the difference between xn and my next value of x. So if I were to say xn plus 1 minus xn, then if I had done Broyden's method correctly and this xn plus 1 was my final guess, then that would just be equal to 0, right? Now, of course, usually when you're doing Broyden's method and iterating through it, as we saw in the last video, that's not the way it always works out. The way it works out more frequently is that you get some f evaluated at xn plus 1. That's going to be equivalent to, well, it's going to be equivalent to my f evaluated at my old guess of xn plus my next guess of what the Jacobian is going to be. So jn plus 1, multiplied by, similarly, the difference xn plus 1 minus xn. So then what Broyden's method says to do is Broyden's method says, well, I'm going to take these values, right? And I'm going to take this top value, I'm going to set it, I'm going to make it negative, and then I'm going to sort of add these up, or subtract the top value from the bottom value, if that makes sense. I might be saying, no, I think I said that in order. But anyway, I'm going to redraw these lines. Oh, can I please redo it? I want to redraw this line. I didn't redraw it that well. And put new parentheses and put a new plus sign. But yeah, cool. So what does this work out to be? Well, this xn plus 1, or actually, I'm going to go ahead and start calling that fn plus 1. So that's just f evaluated at xn plus 1. That's going to be equivalent to, well, it's not going to have anything because that's just a 0. Well, what's that going to be equivalent to? Well, these fxn's are just going to cancel out, and we're going to be left with the difference between the Jacobians. So the Jacobian, my second guess of the Jacobian minus my first guess of the Jacobian, and that's going to be multiplied by the difference between the values of x between my two guesses. But I'm going to go ahead and to simplify it even further and just start calling that delta x. So, in fact, I could even technically call this delta x n plus 1 because it's kind of starting at xn plus 1. So I'll leave it that way, but going forward I'm going to call that delta x. But I'll turn back around and start calling it xn plus 1. And you can see the way I'm defining xn plus 1 is similar to the way Wikipedia was defining it in delta xn. I'm trying to follow the nomenclature so that it's easier to associate it with what Wikipedia says the answer is at the end. So when I have this value of fn plus 1, what do I want to do with it? Well, I guess that's not a super clear question. I could maybe take this difference between the Jacobians, and I could multiply it by any vector of values of x, and I'll maybe call that u. So if I were to say that maybe I multiplied these Jacobians by a u that was parallel to delta xn plus 1, what would that look like? Well, I could say that delta x, the dot product of that and u is just my vector, well, that's going to equal 0 for this case. And so then if that's the case, well, then I could say that, I could say that the Jacobian evaluated at n plus 1 minus the Jacobian evaluated at n is just going to be 0. And that's going to be because this u is perpendicular to delta x. And so because u is perpendicular to delta x, that's telling me that I'm not getting any new information from, well, I forgot to write out part of it. That's kind of funny. Can I? Yeah, I can just undo there. So multiply that by u, that's going to be 0. The Jacobian minus the other guess for the Jacobian is not going to be equivalent to 0. But, yeah. So, sweet. So, looking at all that, I have the difference in the Jacobians times u is going to be equivalent to 0. That's great. Where do I want to go from here? Well, I could go ahead and maybe say that, well, when I evaluate delta x is equivalent to u, or rather, u is equivalent to delta x, what do I get? Well, I would get that the difference between the Jacobians, so j n plus 1 minus the Jacobian at n times u, well, what would that be? That would just be these values times delta x, and so that would just be what we have up here, f of n plus 1. So we've gone ahead and started to sort of build this function here around u, plugging in different values of delta x will give me differing results for what the Jacobians multiplied by this value of u are. And so Broyden came up with a really ingenious way to represent this fact. He said that this is all equal to f evaluated at n plus 1 multiplied by the transpose of delta x multiplied by delta x dot product with itself. And so that times u is just going to be the same thing as this sort of function I have up here. And so let me try to maybe prove that to you a little bit by going back to the scenario. If I have delta x equal to u, I should see that f is equal to n plus 1. Or I should see that this function over here equals fn plus 1. And so what I see, we have these two delta x's. They're going to come together and turn into 1, because it's like the magnitude. And then we're going to have this delta xt times delta x. Or no, okay, so I said that wrong. We're going to have this delta x on top, this delta x being equivalent to u, right? And so that's going to cancel out one of these delta x's on the bottom, and then the transpose of anything divided by itself is just 1. So we would be left with fn plus 1 as like the value of this expression here. So then, similarly, if I took this expression up here and I said that if I said that u is something perpendicular to the transpose of delta x, if you multiply the transpose of something by something it's perpendicular to, you're just going to get a scalar 0. So that would that's what the expression says I am supposed to get. So that is sort of what the matrix math is telling me here. So with all this solved out, where do I want to go from here? Well, if I were to go ahead and say that, well, this value of the Jacobian, or this value of the difference in the Jacobians is just equal to what I have down here because of the nature of the expression, I could go ahead and maybe write this out. So I would say that the Jacobian evaluated at x equals n plus 1 minus the Jacobian evaluated at x equals n is going to be equivalent to f evaluated at n plus 1 multiplied by the transpose of delta x over, this is the delta x dot product delta x, which is actually the same thing as saying the magnitude of delta x squared. That's just sort of like what the definition of that down there means. So with all that in mind, let's go ahead and take a look at what Wikipedia says that Broyden's sort of step is. Yeah, so Broyden's method is telling me that the Jacobian evaluated at n is going to be equivalent to all this over here. And so there's a few things that you can immediately see are similar, and a few things that maybe look a little bit different. First off, if you think back to what I was doing earlier a little bit, and let me pull up a pencil so I can actually write this out. Whenever I say delta xn, whenever I say delta x, what I mean is delta xn plus 1. So if I were to turn that into an n plus 1, n plus 1, you would see a couple things in common and a couple things maybe a little bit different. If I were to go ahead and take all these n's, and then I need to add, if I try to turn the Wikipedia function into what I already have, what I would do is I would take and add 1 to every value of n, so I would say n plus 1, and so that would make all the Jacobians look correct if you move this over to the other side. And then, of course, our xn's would all look correct, so this transpose would be good, this magnitude would be good on the bottom, and those would be good. But we would still be left with something kind of confusing, right? We would be left with, I'm just going to drag this down a little bit, we'd still be left wondering, well, f evaluated at x equals n plus 1, how is that going to be equal to delta fn minus the Jacobian of n minus 1 times the delta xn? Well, let's go ahead and let's look at this term right here, this j n minus 1 delta xn. If I go ahead and look up here, I actually see something pretty similar to what I was writing out before, right? I can see that, yeah, f evaluated at, well, let me see, am I saying this correctly? It should be xn plus 1. Yeah. So I can come up here, and I'm looking at this, and I see that in this function up here is, this function, I can plug this jn times delta x, I can move this f evaluated at xn over, and I can see that this is actually equivalent to part of this top term up here. So if I go ahead and write this out, I could split this up into a couple terms in terms of fn. But then this delta fn, what does that mean? Delta fn is just, well, it should be delta fn plus 1. And that's because I added n plus 1 over here, but I forgot to do that. So this should be the Jacobian of n, which, yeah, that's what I have up in this term up here. And then xn plus 1, that's correct. So that's what I have up here. I was stumbling because I forgot what I was trying to do there. But we can see, we can expand this delta fn plus 1 to be f of n plus 1 minus f of n, right? Yeah, it's just the whatever n is minus 1 minus n. So that I can expand that to be that. And then I can say that that is going to be minus negative, well, it's negative the Jacobian evaluated at x equals n times the difference between the values of x. Well, that should just be equal to f evaluated at n, right? Or it should be equal to negative f evaluated at n, because I do have to multiply. I have to subtract this over to the other side. So then I would just multiply that by negative, or I would make that a negative fn. So you can see this is a plus, these two would cancel out, and I would just be left with an fn plus 1, so the function evaluated at n plus 1. So now all of a sudden, the way Wikipedia ended up writing the Broyden's method makes perfect sense once I evaluate it, because I've just proven that fn plus 1 equals fn plus 1. Or the function evaluated at n plus 1 is just equivalent to itself. So let me move that up just to make sure it's clear. I'm realizing that my camera, I've got one camera in sort of this corner of the screen and one camera in this corner of the screen. So hopefully that wasn't too distracting. But anyway, with that, I have finished up explaining Part 2D. I wanted to say Part 4, but it's Part D. I derived Broyden's method as an iterative refinement of the approximate Jacobian. With that, I finished up homework 2. I'd like to thank you very much for watching, and I hope you have a wonderful day. Shout out to the slouch cam over there. Bye-bye.